What if the next major earthquake on the San Andreas Fault looks nothing like the last one? This is the provocative question raised by a groundbreaking study that redefines how scientists understand fault behavior. By analyzing the 2025 magnitude 7.7 Myanmar earthquake, researchers have uncovered clues that challenge long-held assumptions about seismic patterns, and the implications for California's iconic fault line are staggering. But here's where it gets controversial. The study suggests that future quakes might not just repeat history, but could instead unleash entirely new levels of destruction. And this is the part most people miss. The techniques used to decode the Myanmar disaster might already be reshaping how we predict and prepare for earthquakes worldwide. The March 28, 2025 quake along Myanmar's Sagaing Fault, which claimed thousands of lives and left cities in ruins, became a case study in innovation. A team led by Caltech's Jean-Philippe Avouac and postdoctoral scholar Solène Antoine leveraged cutting-edge satellite imaging to map the fault's movements with unprecedented precision. Published in Proceedings of the National Academy of Sciences on August 11, their work reveals that strike-slip faults like the Sagaing and San Andreas are far more unpredictable than previously thought. For instance, the Myanmar earthquake didn't just rupture a 300-kilometer seismic gap as models predicted. It extended over 500 kilometers, releasing more energy than expected. This defied the seismic gap hypothesis, which assumes that dormant fault sections will slip to catch up on missed movement. But how did scientists track such a massive shift? The answer lies in image correlation, a method pioneered in Avouac's lab. Unlike traditional radar interferometry, which struggles with north-south displacements and signal decay, this technique compares high-resolution optical and radar images before and after an event. By applying it to the Sagaing Fault, the team discovered that the eastern side of the fault moved 3 meters south relative to the west, a shift that reshaped the landscape and hinted at hidden complexities in fault dynamics. This isn't just academic. Current seismic hazard models rely on statistical probabilities, assuming that earthquakes repeat in predictable cycles. But the Myanmar quake proves otherwise. Historical records are like a snapshot of a much longer story, Avouac explains. They're too short to capture the full range of possible earthquakes. For example, a 30-year risk assessment might overlook the fact that a fault could accumulate stress for centuries, only to release it in a single, unprecedented rupture. Physics-based models, the study argues, offer a better path forward by integrating real-time data on slip rates, stress accumulation, and fault geometry. The paper, titled The 2025 Millwave 7.7 Mandalay Myanmar Earthquake Reveals Complex Earthquake Cycle with Clustering and Variable Segmentation on Sagaing Fault, is a collaboration between Caltech, GNS Science, Earthscope Consortium, and Southern University of Science and Technology. Funded by agencies including the US Geological Survey, it underscores the global stakes of rethinking earthquake forecasting. So, here's a challenge for readers. If historical patterns are only part of the story, how can we prepare for earthquakes that defy expectations? Are current building codes and emergency plans enough? Or do we need to embrace radical new approaches? Share your thoughts, because the next big quake might not follow the script we've written.